Да.
Да.
Да. Започваме. Okay. Започваме. Hi all. Thank you for taking your time and join our meetup this evening over the topic of data science in healthcare, extreme scale text-based classification of medical data. I will start with short introduction of who are the organizers, who are our partners, then follow up with the presenters, and we'll give the word to our experts to share with you what they have prepared. First of all, my name is Jana Neikova, and I'm part of Data Science Society. This is fully a voluntary organization, and the team is gathered around the idea of exchanging data science experience and knowledge in combination with lots of fun and interesting activities that we create. We have organized a number of datathons through the years, regular meetups, and like a hint for what's coming next, we plan to introduce also beer afternoons. Follow us up to find out the details, but in the meantime, if you have any suggestions or anything that you think those beer afternoons might be, please contact us and share your thoughts. Our site is datasciencesociety.net, and you can open it to find out more about us as a society, and also ping us if you want to join our team. What's next? I want to say a big thank you to OntoText, who are our partners for today's event and helped us a lot to organize it and make it happen. Most of you, I suppose, already know this company. They are a global leader in enterprise knowledge and graph technology and semantic database engines. To find out more about their solutions and their expertise in the different domains, like, for example, healthcare and finance, you can visit their site ontotext.com, or maybe you can get some hints from Svetla and Anton, who are our presenters today. By mentioning that, I want also to shortly introduce both of them. Christoph currently conducts research and development in the field of NLP at Sirma AI, which is trading as OntoText up to today. He has quite solid background in different areas like document sectioning, text generation, computer vision, large-scale medical text classification. Along with this, he has published a number of publications over the past 7 years, and now works as a computer vision researcher and engineer. Svetla Boycheva, actually Dr. Svetla Boycheva, has a PhD in computer science and now is a senior research lead at OntoText, responsible for conducting research and prototypes development at the company. She has more than 30 years experience in teaching computer science, currently leading AI classes, and being a professor in several universities. On top of that, she has authored also 10 books and a lot of scientific papers through the years. So I believe that both of them have a lot of expertise to share with you. Now, before I give the word to Anton and Svetla, just want to let you know that all the questions would be you can write them down as comments under the direct streaming so that we can follow them up later on our Q&A section. So not to lose more time, Anton, Svetla, over to you to share what you have prepared for us.
Thank you for presentation and organizing this webinar. Special thanks for the overall organization of Data Science Society. I'm going to present our topic, Extremescale Text-Based Classification of Medical Data. This is research funded by European Union Horizon 2020 program, grant agreement 825292. And this is work in progress. This is a joint work with Anton Christoph and with our team. At the end of the presentation, you'll see the full team acknowledgements. First, we'll start with a short introduction to the domain, because I don't know whether all of you are aware about the domain-specific ontologies and classifications which we're using for this task. This is quite important task, and the healthcare data processing is a hot topic. The automatic processing and knowledge extraction from medical records is a task with public importance, but unfortunately, the majority of electronic health records are currently in free text format, in unstructured format, and this task is quite challenging. It requires a lot of natural language processing tools and services which should be trained on specific vocabularies, specific ontologies, because they need to deal with very rich and complex terminology. Unfortunately, there is a lack of multilingual terminology resources and domain-specific ontologies translated on several languages other than English. And today we'll discuss mainly the task for the English language. Here are presented a few examples for clinical texts where are discussed the patient history in anamnesis, and there are mentioned, highlighted with different colors, some disorders in the patient history, diastolic function, heart failure, hypertension, rheumatoid arthritis, etc. You can see on the next example that there are also used some abbreviations like COPD, which means chronic obstructive pulmonary disease, or CHF, which is congestive heart failure, and also some disorders are mentioned with no specificity, more generic description, like diabetes mellitus, without specification whether this is diabetes type 1 or type 2, which means whether it's insulin dependent or non-insulin. Also, for the next example, we can say that they're more complex disorders with not only the main disease, but also the cause of disease and different um, uh, versions of the disease development. The vocabulary for such disorders is quite rich. Usually, the physicians are mentioning and very free way different disorders, and when we need to process clinical texts, we need to deal with such problems like disambiguation. When we need to extract different specific concepts and to integrate the extracted knowledge in knowledge graphs, we need somehow to identify the diseases which are referring to the same disorder. That's why it's better to use URIs, which provide unique reference to the specific concept. And this is really important task when we need to extract the knowledge from textual descriptions and to integrate it in knowledge graphs, because further we can benefit from the integrated data, providing us such opportunities for reasoning, for similarity search, and especially in healthcare domain, we can search not only for similar cases, but also for different phenotypes, or searching more complex relations between the clinical records of different patients. The text-based classification is a process of assigning tags or categories to text according to its content. In our case, we are trying to assign classes from standard classification and ontologies, which are domain specific. Bioportal is one of the main resources where you can see in linked open data a lot of ontologies related into the biomedical domain. Here in biomedical portal, the current status is that it contains around 800 ontologies. And the ontology, which is in our primary interest, is SNOMED. This is the standard nomenclature of medical clinical terms, one of the widely used ontologies in healthcare systems. And it contains more than 360,000 classes. It's quite rich ontology. You can see here some characteristics of SNOMED CT regarding the properties, the organization in depth, number of children classes, parents classes, etc. This is the official website of SNOMED International, which we're using in our research, and we will try to assign automatically SNOMED CT codes to the descriptions, textual descriptions of diagnoses which we extract from clinical texts. Here we can say, for instance, for one of the terms which was mentioned in our examples, hypertension, the SNOMED CT browser, how many references actually found, especially for disorders, more than 280 references for this specific disorder, which means that this description is quite general. which makes it quite ambiguous, and it can refer not to the single SNOMED city code, but to too many SNOMED city codes, because there is no specification what is the type of the hypertension and what is the stage and what is cause. And our objective is to develop methods for automatic association of SNOMED city codes to textual descriptions of diagnosis. Such textual descriptions actually can be quite rich regarding the vocabulary which was used, because different physicians are using different specific terms, and also the number of diagnosis disorders in SNOMED-CT is more than 150,000 classes. The remaining classes in SNOMED-CT are referring to different type of procedures, finding, and other concepts which are not particularly classified to disorders. That's why we restrict our research to those which are referring to disorders only. But for 150 classes, we need a huge training data set for our classification task, and we need somehow either to find such already annotated data set, or we need to create from the scratch such training data set. For so many classes, we need at least 10 examples per class. Even 10 is quite a small number. It's quite challenging task to find such huge annotated data set. Usually clinical data are not publicly available due to the GDPR issues, because they contain private and sensitive data. And there are quite few manually annotated data sets because this is time and effort consuming, and usually the medical experts are quite busy with other daily tasks related to the healthcare practices. And we need to rely only on publicly available sources. That's why we decided to use other standard classifications and ontologies as references to the textual descriptions of diagnosis and some open data. The other classifications which were selected are also widely used. International Classification of Diseases, 10th modification, clinical modification. This version is translated on several languages. Even in our country, its version on Bulgarian is used. And this is the most widely used statistical classifications. It contains more than 90,000 classes. It's public, and the major problem with this classification is that it's statistical classification, and the class names are not referring to particular diseases, but to classes of diseases, which means one class contains several diseases. Here is the reference to the official website of the World Health Organization. Currently, it was issued 11th version as well. Another classification which we're using is human disease ontology, which is again quite rich, containing more than 70,000 classes. And let's see what happens with hypertension browsing on those on the latter two classifications. Here we see again a huge ambiguity because for hypertension there are too many classes also in ICD-10, even its statistical classification. For disease ontology, again we have a lot of classes regarding the hypertension, and we can see also that there are references between different ontologies and classifications, and also here are provided some synonyms like high blood pressure, hyperpressure, hypertensive disease, etc. And references between the ICD-10, SNOMED codes, etc., which actually gives us an idea to search between different mappings of ontologies in order to identify more examples which are annotated with reference codes to SNOMED CT. Here is given an example with one of the diseases which was mentioned in our clinical texts for bronchiolitis obliterans organizing pneumonia. Here we can say that in ICD-10, which is statistical classification, there is no particular code referring to this disease, but there is a class which actually refers to it, and we can say that the class other specified chronic obstructive pulmonary diseases is quite general, and there is no even single word in the class name and in the particular disorder which are common. They are quite different. In general, the descriptions of disorders can be really different, and we can't search by keywords in the general case. That's why we decided to select some of the widely used ontologies and standard classifications like SNOMED CT, Unified Medical Language System, Medical Subject Index, disease ontologies, International Classification of Diseases 10th and 9th version, also International Classification of Diseases for Oncology, Orphanet for Rare Diseases, MONDO, which is Monarch Disease Ontologies, harmonized version for description of diseases, and to start searching for different mappings between them in order to generate our data set. For those mappings, we used as intermediate source Wikidata, which is really rich source of semi-structured information. Here we can see for COVID-19 that we have not only description of the term and the label, also we have different synonyms, and it supports also multilinguality. We can see also for Bulgarian, the description, the names, synonyms, and for many other languages. It also includes for the majority of the terms mappings to different standard classifications and tautologies with the reference codes. Here we can see for COVID-19 the ICD-10 code, also here is the MESH code, and there is available also SNOMED code, etc. This resource allows us to use different Sparkle queries in order to harvest the data of interest. and this is a sample Sparkle query for searching of SNOMED descriptions of diseases and their corresponding SNOMED codes in Wikidata. Unfortunately, the first result gives us that there are only around 700 disorders with their referencing codes in Wikidata, which is quite a small number of disorders. This is quite insufficient for our needs. That's why we decided to search and to combine different sources, ICD-10, human disease ontology, SNOMED, and to include here also the mappings between different codes for different ontologies. Also, there are descriptions and synonyms. We can also include in our search not only the labels of the terms, but also descriptions and different synonyms, which gives us more than 52,000 results. This is now more promising result, but we can say that some descriptions like this one, human disease, is not quite helpful. And for some of the terms, they're missing descriptions, missing human disease ontology codes or SNOMED codes, which gives us some insights about the current status of the data in Wikidata. They're not well mapped and connected. This is not the only reason. There are also some other reasons for such missing information. In general, there are no one-to-one mappings between any two classifications and ontologies, because they serve that they actually exist for different purposes, and they present from different point of view the information. For some of them, we have one-to-one mappings for some of the codes and terms. For instance, here we can see mappings between ICD-9 and ICD-10. For some terms, we have such one-to-one, but for the other terms, we have one-to-many or many-to-many, or even for some codes, for some ontologies, there are no existing mappings. We used different rules for mappings between ontologies, not only those collected from Wikidata, but also from the official websites where are published ontologies and guidelines for their mappings. And we created an algorithm for mapping between the selected ontologies and populated the data from the selected ontologies, mappings between different sources in Wikidata, and etc. And our current data set, the first version, contained more than 22 million data records with 128,000 SNOMED codes. Unfortunately, this data set, which was not surprising, was highly unbalanced, and it didn't serve well our classification task purposes. That's why we needed some techniques in order to cope with this highly unbalanced data set. For some codes, we had just single descriptions. for some codes, we had more than 10,000 descriptions. For the other codes, we had quite few descriptions, but again, those descriptions vary from 2 to 2,000. And this actually causes a lot of problems in the classification algorithms. We needed more data, but adding more data from different sources caused more problems because some of the data sets actually were not spread among several SNOMED codes, but they were grouped to small number of codes. For instance, orphanet, these are rare diseases, genetic diseases mainly, they were grouped to quite few SNOMED codes. And this caused high imbalance of our data set. Also, we needed a lot of data cleaning with such general descriptions like human disease, which was generated from Wikidata, and a lot of problems with cleaning the overrepresented and underrepresented classes. In order to deal with the underrepresented classes, we used data augmentation. The original idea for dataset enlargement was inspired from the images for neural networks training, where were used popular techniques like flipping, rotation of images, scaling, cropping, translating, pixel regions changing or filling with constant pixels, or pixels region swapping, etc. What are the types of augmentation that are applicable for textual data? We used some of the following techniques: swapping random letters within a single word, swapping random words within a textual description, replacing words with its synonym. This is quite challenging, especially for medical terms. That's why we had quite few examples for such technique application. Deletion or insertion of random letters within a single word, replacing random letters with a letter close to it on the keyboard. The latter two are quite common, like typos, when the physicians are typing the text and the clinical narratives, because usually when we're processing data, we suppose that they are going to be clean, but in general, in the raw data, we have a lot of typos, and introducing some noise in our data, in case the percentage of this noise is quite low, it's not a huge problem. It will help a little bit to our method to deal with small typos. And in order to deal with this highly unbalanced data set, we decided to split it on more focused subgroups, like codes which are dealing with disorders, with procedures, and with findings. This allows us to have three more balanced data sets, because procedures are quite balanced data set, and findings, and still some problems with disorders were available, but this is the group with the majority of SNOMED codes in our data set. That's why we filtered some data which were a little bit noisy or not in our target disorders group, and this was our current version. It contains more than 100,000 codes for disorders, about 67,000 for procedures, and 70,000 for findings. And now I will give the floor to my colleague to present the text-based classification.
Hello, I'm Anton, and I'm here to present you the basic steps behind text-based classification. The idea here is all of you to gain some intuition of the ideas and methods part of this NLP problem. The information presented will be simplified and mathematical details will be avoided in order not to distract those of you who are just entering the field. For you who have knowledge in this field, I believe my final slides will be of your interest. Unstructured text is everywhere, such as emails, chat conversations, websites, and social media posts, but it's hard to extract value from this data unless it's organized in a certain way. Doing so used to be a difficult and expensive process since it required spending time and resources to manually sort the data or creating hard-coded rules that are difficult to maintain. Text classifiers with NLP have proven to be a great alternative to structured textual data in a fast, cost-effective, and scalable way. So, text-based classification is also known as text tagging or text categorization. It is a process of categorizing text into some predefined categories. There exist three main methods of extracting valuable information from a text by which we can construct our task. These methods are binary classification, multi-class classification, and multi-label classification. So what these definitions stands for? Next slide. Binary classification is trying to predict a label for every text sample and must choose this label from two possible ones. Here's a small example in the table. Given this dataset, our binary classification task will be to find the sentiment or emotion behind our customer reviews. Every review can be classified as positive or negative. Next slide. Multi-class classification is trying to predict a label for every text sample and must choose this label from number of possible classes. Given this dataset of movies and their ratings, our multi-class classification task will be to predict these ratings, which will be between 1 and 10. So our problem here has 10 classes. Next slide. Multi-label classification is trying to predict one or more than one labels for every text sample and must choose this label from number of possible classes. Our example again is in the field of cinema. Now we should predict movies genres. Once in the table depicts if the current movie belongs to this specific genre. Okay, next slide. Now I will talk about classification models. Next slide. We have already know what is text-based classification and its three major methods of constructing the NLP problem. Now we need a model which can solve our specific task. One such model is BERT, which stands for bidirectional encoder representations from transformers. You can check the reference at the bottom of the slide to gain more detailed insights of this model. Next slide. Why was BERT created? One of the biggest challenges in NLP is the lack of enough training data. When a researcher trying to solve almost every NLP task, he or she end up with a very small dataset. The sizes of commonly created datasets vary between 1,000 to few hundred thousands. Unfortunately, in order to perform well, deep learning approaches require much larger amount of data. A lot of improvement can be observed when we train our deep learning models with millions or more annotated training examples. To deal with this problem, researchers developed various methods of using unannotated text, which can be found on the internet. Then these generated purpose models, then these general purpose models can be fine-tuned on smaller custom datasets. One of these general purpose models is BERT. This approach results in great accuracy improvements compared to models trained only on these small custom datasets mentioned earlier. Next slide. So what is BERT core idea? Its task is to fill the blank spots based on the context. For example, if you have the following sentence, the movie is very boring. If you mask the word boring, BERT language model will try to figure it out. So this general purpose BERT will be trained on annotated free text. Around 15% of the words in this training corpus will be masked, and the task will be prediction of these masked words. Bidirectional means that the model looks in both directions and it uses the full context of the sentence, both left and right surrounding words, in order to predict the masked word. At the end, we'll come up with precise general language model that can be used for fine-tuning over different datasets and on different NLP tasks. Detailed explanations of the architecture's modules can be found in the BERT's paper. Next slide. BERT's core component is a transformer, which is a tension mechanism contextual relationship between words in the text. Since BERT's goal is to generate a language representation model, it only needs the encoder part. In order to perform text classification with BERT, we need first to perform pre-train BERT on our new dataset. Second, to add a classifier on top of the BERT's output to make the predictions. Next slide. The main BERT's advantages are its incredible performance. It can be used in real time. It is open source. Since big corpus of medical data is something a dream, it's very suitable to be pre-trained with small amount of specific medical data. Next slide. There are different versions of BERT pre-trained on custom data which are available. These are BioBERT, Multilingual BERT, Slavic BERT, Clinical BERT, and PubMed BERT. We can see the papers related to all of these pre-trained models. Next slide. I'll talk about embeddings now. Embeddings is a term used for interpretation of words for text analysis. Their form is a vector of real values. These vectors encode the meaning of the word such that words with similar meaning will be closer in the vector space. So the embeddings projects information presented by text into some n-dimensional vector space. In the example, we have two-dimensional embedding vector space, which encodes these similar words in closer positions. Illustrations represent visualization of these words embeddings. Students, school, and university have similar meaning, so their embedding vectors are closer in the vector space. The same goes for dog, cat, and fish. Next slide. Where we can get these text embeddings. BERT is basically a trained transformer encoder stack. Every transformer encoder takes a sequence of words as input and outputs a vector of specific size. These vectors can be interpreted as embeddings since they hold contextual information of the input text. Next slide. Next slides are related to extreme scale classification problem. This is a task of dataset classification with extreme number of labels. If we have an unbalanced dataset or we want to split our problem into subproblems, we can group our labels into clusters and train a model to predict to which clusters every sample belongs. Label clustering is widely used in extreme scale classification problem because datasets are mainly unbalanced and there are a vast amount of classes. Let's say more than 10,000 classes. This can be formulated as binary, multi-class, or multi-label classification. The illustration shows a multi-label classification idea where one sample can belong to multiple clusters. Labels clustering also can be used where classification can be done with less granularity. Next slide. Here is the workflow of the extreme scale classification task. It's very difficult to train one model to perform predictions with high precision. It is more convenient to split this problem into subproblems. First, to train a model to predict to which clusters every sample belongs. For example, sample 1 belongs to cluster 1 and cluster 2. And then train second model or models to refine the predicted clusters into labels. This refinement will output probability of every label from the selected clusters. Next slide. Here I want to show you the steps needed for cluster-real datasets labels. First, we should create labels embeddings and then apply clustering algorithm. Next slide. Matrix L represents these label embeddings. So how to compute this matrix? The slide shows a minimal example with some data. Embeddings were calculated on all samples, which are all the descriptions in our data. This is metric X. Every row represents a sample's embedding. When we transform the labels of each example by multi-hot encoding, and we get matrix Y. This means that if we have a total of 4 labels in our dataset, sample 1, looking at the first row of the matrix, has labels with indexes 0 and 1. These are first and the second column of the matrix. Labels embeddings, matrix L, is calculated using dot product between X and Y. This matrix L gives us information on how each label relates to each sample in our data. And this is very valuable information. Next slide. Once we have calculated the L matrix, the selected clustering algorithm is applied on it to cluster the labels. You can choose the algorithm that best fits to your task. Maybe k-means is the most commonly used one. The selection of the clusters number can be done by grid search until finding the optimal number based on the distribution of the data. Next slide. Last step of our workflow is the refinement. There are lots of possible solutions and there are the most commonly used. Classical shallow artificial neural network, deep learning approach, and binary classifiers for every label. We can apply a classical shallow, some sophisticated model, or we can choose the third one. It's all about our dataset. So we can choose which best fits our task. That was for me. Maybe Sveto can continue with the acknowledgements.
I would like once again to thanks to Data Science Society for organizing this webinar, to acknowledge our sponsors, funding project Taxbased, funded by European Union Horizon 2020 grant, and all my colleagues in the project team, Alexander Tevchiev, Andrei Abramov, Christo Papazov, Pavlin Gurov, Todor Primov, and Stanislav Slavkov. And to thanks also to Ontotex for the overall support. Please visit the websites for more insights about different organizations and projects. And thank you. We're open for questions.
Hi, thank you, Svetla and Anton, for the quite detailed presentation. Following our channels, seems that our audience is a little bit shy in terms of sharing their questions. In the meantime, if anyone decides to ask his or her questions, I would like to ask you a few of them. Starting from the more general one, you gave quite detailed explanation of your research and models and methods used, different types, etc. But what were your biggest limitations or obstacles through your way in terms of defining your work? If you can share.
In general, the lack of data sources, this is the major obstacle in data science, and the need to generate from scratch training data set for such a complex domain without any expertise knowledge in the domain. This was really challenging task when I needed to start searching data and learning more about the domain-specific ontologies, how to map them, how to generate such huge training data set, because deep learning methods are quite expensive. They require a lot of training data. And especially when you deal with several thousands of classes, you need for each class a lot of data. The most challenging part. And the next part probably is the training of those methods, because underrepresented classes are just skipped. They are not presented, and the overall performance drops significantly due to such underrepresented classes, because the overrepresented classes actually takes the advantage, and this is the most challenging part.
Thank you. Yes, actually, those points are always valid for data science, for better or worse. And I suppose also it was quite time consuming to go through the whole way till you have some final good results. My next question is a little bit more detailed, if I may say so. Could you please share if the proposed approach can be applied to a different language than English, because we all know that English is like the worldwide most common one. And in addition to that, how easy would it be to adapt the model and the data for another languages so that they can be generated?
Unfortunately, the majority of standard classifications and tautologies are not translated to other languages. They're just few translations of Nomad CT to Spanish and French, and not available, for instance, for Bulgarian. ICD PAN classification is translated to the majority of European languages. But the data available in Wikidata lack the translations to many languages. We can benefit from the multilingual labels in Wikidata, but for quite small data set. And another approach is to use some machine translation algorithms, but for such specific terminology, again, there are some problems with the translations, because such machine translations method usually use the most common vocabulary and not the medical terms, which makes the problem quite challenging. Still, we can generate automatically some data set, but not so huge like for English language. And regarding the methods, probably Anton can share some insights for different types of transformers.
BERT can be applied to different languages, but as Seto says, the data are important part. So if we can get some data from the specific language and specific medical terminology of that language, we can pre-train some BERT model to work with this data.
Yeah, one approach is to crawl some data from the web related to the medical terminology in the specified language to fine-tune the BERT model, for instance, the multilingual BERT model, to deal with the specific terminology for the target language. And that's it. This is like a BioBERT, but for the other language.
I saw that there is a new question in the chat. The question is, did you try GGP2 from OpenAI to apply in our case? We choose BERT, and especially its pre-trained version BioBERT, because it's already trained on medical terminology. So for us was a little bit easier to use this, because we can pre-train it easily, not to train from scratch. And the second reason is that BERT is very fast, so we can apply it in real time. There are a lot of alternatives of BERT, like GGP2 or ExcelNet, which are very accurate, but their processing time is a pain in our case. We need to work in real time.
Yeah, because I didn't mention, but our overall aim as the trained model to be integrated with health information system and to work in real time when the physician is typing the diagnosis automatically to be associated with codes, which is a real-time task, which requires solutions which are quite efficient, and the time is crucial.
Thank you both for your answers. I actually have one more question for you, which is more which is closer to BERT models, which you touched a little bit before. Which of the discussed BERT models showed the highest accuracy in the classification tasks? You referred to several of them, I think five plus minus one. And which of them can be used for, again, referring to my first question, which of them can be used for any language apart from English? Because there are still some countries and nationalities who keep themselves tied to their mother languages. Share.
In general, all the clinical documents are written on the local language, which means each European country needs such models for their domestic language. And this is a really important problem. In our experience, the pre-trained model for multilingual bird fine-tuned with some texts on domestic terminology as the best one with higher accuracy. The next one, surprisingly, is BioBird, which is pre-trained with medical terminology for English, but when it's fine-tuned for other language than English, it can actually easily adapt to the language model for other languages and can also be used successfully for other language than English medical terminology classification. The other models are more specific, like Slavic bird is quite specific, but trained to quite common vocabulary and to the small number of documents, which requires much more training and fine-tuning, and we didn't succeed to fine-tune it with sufficient accuracy. And the clinical bird, even it was pre-trained again to PubMed, which contains the scientific publications in medicine repository of such data. It again didn't scale up quite good for other languages.
Thanks, Vetwa. And referring to your reply, is there an option for you to share what metrics you managed to achieve, or give us a hint about that in terms of precision, for example, from what you just described?
Actually, for the highly unbalanced data set, the first one with 22 million, we gained more data, but it was more pain to train this data set, which was highly unbalanced, and we didn't achieve the quite good accuracy. It was just around the 50% accuracy, but for the more specific data sets which were splitted and cleaned well, we had better accuracy, starting from 60-70% per different types of classes for disorders. Procedures and findings. The maximal accuracy which can be achieved is 85% due to the huge number of classes, because still you have some classes which are underrepresented, which cause the significant drop of the accuracy.
Thank you. Thank you about this additional feedback. And maybe one last point. After all the work done and all the trainings and models, etc., how can this not data, but this outcome and findings and final results from the models be used after the text classification, and maybe it's real life application, if you can share? This is again something more general, but kind of important, you know.
Yeah, thank you for this question. We didn't mention actually our overall goal of the project because this was not the main focus of this webinar. The main application of the proposed solution is First of all, for automatic extraction and concepts normalization from clinical texts, especially for disorders to SNOMED city codes. And the structured information actually can be used for knowledge graph representation, where the SNOMED codes are represented like URIs, which allows us to have disambiguated concepts from the clinical narratives, which allows the patient records to be integrated in one knowledge graph and to be able to search for similarities, to do different types of reasoning or knowledge graph embeddings, to search for more complex relations between different patients' current status and diseases development and causes for diseases. In general, this is part of, as I already mentioned, the research project, and the overall solution will be integrated in decision support system, integrated with hospital information system to support the medical experts in their daily work.
Okay, thank you very much about that. I think that the presentation and all your additional replies were quite detailed. For the time being, I don't have any other questions, and I also don't see anything pending on the live chat. So from the from Data Science Society side, I want to say a big thank you for to On2Text for supporting us for this webinar. Special thanks for Svetlana and Anton for all the work done in the presentation prepared and sharing their expertise. Last but not least, everyone who registered on our page will receive follow-up materials, inclusive the link to the presentation that we just went through. And of course, if anyone has any other questions which come a little bit late, you can always ping us on our social medias, and we'll do our best to support you and give some replies. And yes, what's next? We'll soon introduce our next event, next webinar for a month, June. The topic and the presenters, and also a reminder for you to think about the beer days and let us know how do you see them, and if and to see and also follow us to see what we want about that. Thank you and have a nice evening.
Thank you. Have a nice evening.
Bye.
Bye-bye.
Bye.